guys. Okay, so we are going to now in chapter 8 continue on with the gas laws, and we have here Boyles Law, Charles Law, Lussac Law, combined gas law, Avogadro's law. Then we're going to look at the STP, which is a standard in the molar volumes, and then ideal gas laws and the reactions, which is a stoichiometry, and the Dalton's gas law. And as you can see, the different conditions. So Boyles studied the relationship of pressure and volume, keeping the temperature constant. Charles studied the relationship of volume and temperature, keeping the pressure constant. Lussac studied the relationship of pressure and temperature, keeping the volume constant. And combined gas law is basically combining the Lussac's law, the Charles law, and the Boyles law into one formula. Okay, Avogadro's law talks about relationship of volumes and the number of moles, keeping the pressure and temperature constant. Then the standard temperature, pressure, volume values, all these are also given in your handout on the last page. Okay, now ideal gas law, where we talk about the gas constants. Okay, and all these things that you see were constant above. You see this, the temperature was kept constant here. The temperature is kept constant here. Pressure is kept constant. Volume is kept constant. Okay, and here pressure and temperature are constant. So the gas constant is representing these constants. Okay, then we will talk about the stoichiometry, which is the gas laws in a chemical reaction, and then the Dalton's law, where we're looking at the partial pressure, the total pressure and the partial pressure. Okay, so now the last part is the vapor pressure. Okay, and boiling, but that relates more to the solutions. So we are going to look at this part in the next chapter, not in this chapter. Okay, let's look at the Boyles law first of all. So anytime we are doing these gases, we're studying the gases and we're trying to quantify a gas. So what we do, we generally put them in the syringe. Now in the syringe, there is a regulator. Okay, the regulator measures the pressure in atm. And now what you're doing is, let's just make this here clear a little bit. Let me erase this. Okay, so here we have the syringe, which is containing, we pulled some of the gas in the syringe, and this gas is at a certain volume. This gas has a certain volume, and this volume is noted down. And generally these syringes, they have these markings here, which are generally in milliliters. But remember that anytime you're doing these gas laws, the volumes are always converted from milliliters to liters. So milliliters to liters. And whenever this is done, we know that 1 liter is equal to 1000 milliliters. So this is the conversion factor you're going to use when you're converting the milliliters to liters. Okay. Now, when we talk about these gases, we have put this gas in a syringe, and now we are first of all going to take the volume, measure the volume of this gas in the syringe, and that is your volume, first volume, and note down from the regulator reading what is the reading of the pressure. Okay, now that pressure relates to the weights that we put. So here we are going to put the weights, so that weights get translated to the pressure in atms. So note down that. So this is your first reading. Okay, you start with that. And next is you increase the weight. So as you add the weight, the piston begins to move down and down and down. And as more and more weights are added, as the piston moves down, this is your reading V1. Next reading is V2, the third reading is V3, the fourth reading is V4, and it is also depending upon, how much of the weight is added and how much of the piston moves down. So it depends on the nature of the gas also. Some gases are very easily, they get squished, but some gases, take longer to squish, but nonetheless, all gases can be compressed, right? So now what happens is, every time you see a new reading of the pressure, you note that down. But here's the thing you see, as the volume decreases, the pressure, or in other words, as the pressure increases, the volume decreases. So first the pressure was 1 atm, the volume is 100. Next, you increase the pressure and it reads at 1.25 atm. The pressure is lower than 10 ml. So it's 80 ml. Next is, let us say, you increase the pressure more and you increase the weight more. You know, you add the weights more. These weights are going to translate into the pressure on the regulator. And you see, you read that pressure, it's 1.50, but the volume on the syringe is reduced. And then last is, you know, we can just only go up till a certain point, because some gases, they easily convert to a solid. That is they can solidify, but there are some gases they can liquefy. So whenever there is a change of state, that's the gas law doesn't apply. So what we see here is that as the syringe moves down and down and down, the volume keeps decreasing, and a time comes when you cannot do this anymore, because you just maxed out. After all, gases are gases, you know, they're mass, they occupy space. So now we see a relationship here, which is as the pressure increases, the volume goes down. So there is an inverse relationship between pressure and volume. And we show it by this formula, P1, V1 is equal to P2 and V2. Okay, so this is how you're going to, you know, get this. So keep this in mind, that the pressure readings are going to be in ATMs, generally in ATMs. But if they are in millimeters of mercury or in PSI or you know, torr, then you change it. Okay, now if we were to, I'm going to just do a simple algebraic conversion just for a reminder or just to review. So P1 V1 is equal to P2 V2. Okay, now here what do we see? If we were to find the value for P1, then how are you going to change it? So we want P1, but we want to get rid of V1. So what do? V1 over V1 cancels out from here, and here you get P2 V2 over V1. So this way you're going to get P1 is equal to P2 V2 over V1. Okay. On the other hand, if you were to find for V1, you would do the same thing, you know, so it's the same process. Okay. Now let's look at this problem. The problem number, it's a study check problem, 8.3, page 296. So here is this page 296, page 296, and this is the problem number 83. Study check is 8.3, sorry, 8.3, not 83, 8.3. Okay. In an underground natural gas reserve, a bubble of methane, so this is a methane gas, is CH4. A bubble of methane gas has a volume of 45 milliliter. Volume is equal to 45.0 milliliter. Okay, and at 1.60 atm. So the pressure is 1.60 atm. Okay, now what volume in milliliters? Now sometimes you don't need to convert. If they are asking you to convert, if not asking you to convert, then you leave it as. If not asking, then don't convert. Then don't convert in Boyles law, when applying Boyles law only. Okay, otherwise you need to convert. Okay. Okay, now, so in milliliters, so find the volume in milliliters. What is the volume in milliliters? What volume in milliliters will the gas bubble occupy when it reaches the surface where the atmospheric pressure is? Now here you are given the atmospheric pressure of 744 millimeters of mercury. 744 millimeters of mercury. Okay, if there is no change in the temperature or the amount of gas. So here, by any means, the temperature is not changing. So temperature not changing. Okay, it is remaining the same. All right, now T stands for temperature. So something I'm going to write down here so we don't, so P is for pressure. V is for volume. T is for temperature. And N is for moles. What else? R is the gas constant. You know, we have that. Okay, so these are the basic things. All right, now we are going to look at this problem. So first of all, this is in ATM and this is in millimeters of mercury. So you need to make the units same. So make the pressure units same. So you can change either one, but it's best to keep an ATM. Okay, so make the pressure units same. So what do? So we know that 1 ATM is equal to 760 millimeters of mercury. Okay, so we need to convert this guy to ATM. Okay, so how do you do that? So 744 millimeters of mercury times 1 ATM. This is what you need over 760 millimeters of mercury. Okay, so let's do this calculation. Okay, so when we do this 744 divide by 760 and these millimeters of mercury cancel out, we get 0.97 ATM. Okay, so next thing is we are going to set up this problem. P1, we always write the formulas. Always, let me write this in red so you understand this, that always write the formulas for the gas law. Okay, when you show in working. Okay, so here we have P1 V1 is equal to P2 V2, which means that the P1 V1 is the you know, sorry, where was it? So P1, so here is, this is V1, P1, V2 and P2. So here we see that the volume is, so this becomes 0.97 ATM. Okay, so the pressure is decreasing. So ideally, you should see that the volume should increase. So how does this happen? So we need to find the V2. Okay, we need to find V2. This is what we need to find. So we are going to now set up this problem as P1 V1 over P2 is equal to P2 V2 over P2. So here we have this guy removed. P2 and P2 are gone. So now we have V2, and that's what we need to find. So just plug in the numbers. P1 was 1.60 ATM, 1.60 ATM multiplied by V1. The V1 was 45 milliliters, 45.0 milliliters. I mean, ideally you should be converting it, but since the question just wants you to answer it in milliliters, so don't change it then. Then comes the P2. P2 is 0.97 ATM, 0.97 ATM, and that is equal to V2. So here we see that ATM and ATM cancel out, and you're just left with the units of milliliters. So let's do the math here. Okay, I just want to point out here one thing. This answer here was 0.978 and so forth. So this can be rounded up. Okay, and we need to round this up, and this becomes 0.98 ATM. So if you don't round it up, it's a little bit off answer, which is also fine. But if you round it up, then 0.98 ATM. So now you're going to use this 0.98 ATM here, and then you get the answer 73.46 and then you can round this up again, 73.47 milliliters. 73.47 milliliters, or you can further round it up to 73.5 milliliters. Okay, 73.5 milliliters. So that's the answer. Okay, so that's one thing. Okay, now the main use of Boyles Law, the applications of Boyles Law. Applications of Boyles Law is in your own lungs and the diaphragm. So if you feel it, applications in your own lungs and the diaphragm, your own lungs and the diaphragm. Now, diaphragm pushes on the lungs, okay? So that means when the diaphragm is contracted, which means the loss in volumes, then it pushes on the wall. So that when you put the pressure on the diaphragm, when you increase the pressure, when you push the diaphragm, that means you are increasing the pressure on the diaphragm. And when the pressure on the diaphragm is increased, what happens to the lungs? The volume of the lungs goes down. Okay, so you can try this. You push it. That means you are exhaling. You exhale the air out. Okay, so that means you're breathing out. Breathe out. Breathe out. But when you breathe in, you're relaxing your diaphragm. And when you're relaxing your diaphragm, the volume is increasing, right? Less pressure. So the more pressure on the diaphragm is coming from, when you push the air out versus taking in the air. So you can try this at home. So breathe in and breathe out. And you can have a feeling of it on the diaphragm and the lungs, how the Boyles Law goes on there. Okay, next, let's look at now the Charles Law. Now, Charles Law is, in Charles Law, they studied the relationship of volume and temperature, keeping the pressure constant. Okay, so when the pressure is constant means this whole thing is going to be done at room temperature. So how was this done? So let me set up the apparatus. Okay, so here we have this setup. So in the situation 1, the temperature is very low. Okay, when the temperature is low, what we see is that, or we can just say that we have started heating it. So what we see is that there's a certain volume a gas has. And as you increase the temperature, the temperature reading rises and the piston also moves up and up and up. And if you continue to heat it, it's going to obviously pop out and explode. But when the temperature is, as the temperature is increasing, we see then that the volume also increases. So this is one piece we see, that when the volume increases as the temperature increases, and the volume decreases when the temperature goes down. So let's just, instead of this guy, now let's put this in a cold bath or a cold container. So in a cold container, or when they reduce the temperature, what do you see? You will see that the gas begins to contract. So this situation is when the temperature is low, when the temperature is coming down, and the temperature is coming down, the volume is reduced. When the temperature goes up, so this is the T degrees Celsius for the thermometer, and the thermometer is kept to measure the temperature of the gas. So when the temperature goes down, the volume goes down. When the temperature goes up, the volume goes up. So there is a direct relationship. And here in the Boyles Law, we saw that there was an inverse relationship. Sorry, this should be, what am I doing here? This was a direct relationship, but I said it inverse. Sorry, inverse is written like this, my mistake. Sorry about that. Please fix it in your notes. Okay, so inverse relationship is like this. And the direct relationship is like this. Okay, so the formula is V1 over T1 is equal to V2 over T2. So as the temperature increases, we see the piston moving up means the gases expand and they push the piston. But when the temperature goes down, the gases contract and the piston also comes down. Okay, so here we see that in this case, there is this inverse relationship. And let's look at this problem of Boyles Law on page 299. So this is the study check problem. And that is 8.4. And this is on study check 8.4, page 299. Page 299. Okay, what do you see here? Here we have this problem. Okay, a mountain climber with a body temperature of 37 degrees Celsius. So just write down first here all the things that are given. And we will put T1 and T2 later on. So here the body temperature is 37 degrees Celsius. And it inhales 486 milliliters of air. So the volume is 486 milliliters, okay, of air at a temperature of negative, let's read this first. A mountain climber with a body temperature of 37 inhales 486 milliliters of air at a temperature. So the air is at a temperature of, so this is something, keep this here. Inhales the temperature, inhales 486 milliliter of air at a temperature of negative. So temperature of negative 8 degrees Celsius. So this is one piece. So this is the temperature of the air. Pay attention to air. So this is the way it's worded. It's a little bit sometimes, confusing. So here, so a mountain climber has a body temperature of 37. So this is the mountain climber with the body temperature of 37 degrees Celsius. Okay. Inhales 486 milliliters of air, and that's the man. Okay. Of air, and the temperature of the air is negative 88 degrees Celsius. What volume in milliliters? So find the volume in milliliters. Volume in milliliters will the air occupy in the lungs if the pressure and the amount of gas do not change. So here we see that the temperature 1 is negative 8 degrees Celsius. Now, something it's important to point out is that the temperature should always be in Kelvin, and ideally volume should be in liters, ideally, but temperature Kelvin means that anytime you have degrees Celsius, you're going to add 273 to it, and that's going to make the temperature to Kelvin. Okay, and then if it is something is given to you in milliliters, you're going to multiply that by 1 liter over 1000 milliliters to do this conversion. Okay, and let me move this a little bit further away so it's out of the way. Okay, so these are the important pieces for the Boyles Law, that the degrees Celsius has to be converted to Kelvin. So that is 273. You are going to basically subtract 8 from it. So this becomes 265 Kelvin. 265 Kelvin. Okay. And since the question is asking, find the volume in milliliters, so you don't change it, listen to the question. So if they're saying don't change it, then don't change it. Don't worry about it. But in general, the temperatures have to be changed all the time. So 273, they're not going to ask you. So 37 plus 273 is 310. 310 K. Okay. Now, write down the formula. V1 over T1 is equal to V2 over T2. Okay, so here V1 is 486. So we need to find the V2. So let's just do the transformation right here only. So we see that V1 over T1 times T2 is equal to V2 times T2 over T2 here this way. So here you cancel out the T2 from this side and you're left with V2. So now just plug in the numbers. So V2 is what we are finding is equal to V1 over T1 times T2, which means V1 is 486 milliliters over the T1 is 265 Kelvin times 310 Kelvin. Okay, so 486 times 310 divided by 265 is equal to 569 milliliters. Okay, so important thing here is the conversion. Always convert here. Convert, let me write down here. Always convert temperature T degrees Celsius to Kelvin. Okay, and so by adding 273. So this is how you will do it. Okay, now that was the study check problem for the Charles law. Let's look at the Gay-Lussac law now. So we will look at the Gay-Lussac law. Oh, sorry, what are the applications? We've got the applications here. Applications of Charles law. The applications of Charles law is in hot air balloons. Hot air balloons. So in a hot air balloon, what happens? You have this hot air balloon and you have this gas which is burning here at the bottom. And generally it's the hydrogen gas or some other gas, you know. So when this gas is heated up, when this gas gets heated up, what happens to this gas? You heat this gas, right? There is a certain volume this balloon is. And what happens is that as the temperature, as the gas heated up, as the temperature increases, the balloon begins to expand. Why? Because the gas gets heated up. So when the temperature increases, kinetic energy in the molecules increase, collisions in the molecules are going to increase, collisions among themselves and against the wall of the container. So collisions against the wall of the balloon increase. Okay, and when that happens, then the balloon actually begins to inflate. So balloon begins to inflate, and then what happens when the balloon inflates? Then, you know, the gases, when their density also decrease. So in other words, the gases, when heated up, becomes lighter. So gases, when heated, become lighter. And when they become lighter, what happens? They expand. And then they move up. Okay, and then the collisions are also increasing. So they become lighter, they begin to move up, right? And as they move up, the balloon begins to rise up also with them, because the gases are all inside the balloon, right? So they are trapped inside the balloon. So it's just the hot gases, lighter gases, they begin to move up, and that's how the hot air balloon, you know, and when the temperature increases, the volume of the gas is also increasing. The volume of the balloon is also increasing. Okay, so this is the application of the hot air balloon. Now we're going to look at the Gay-Lussac law. Okay, so here is the Gay-Lussac law. Now Gay-Lussac, he studied the relationship of pressure and temperature, keeping the volume constant. So here, anytime you have the pressure and the volume, so keep sure that pressure, generally ATM, generally millimeters of mercury. So these commonly we use these, and the temperature always T degrees Celsius is converted to Kelvin. So that means whatever the value of degree Celsius is, you have to add 273 to it in order to do the conversion. Okay, now how is this done? Let me set up the apparatus. Okay, so this is how you set up the apparatus. You seal the gases in a container. So these are the gases inside a container. And the containers have the regulators on the top that reach the pressure. And now you have kept the gases, this setup, the setting at, in these different settings of the temperature. So here the temperature is very high. Here the temperature is very low. And this is just a normal temperature, normal room temperature. RT, room temperature. Okay, so what do you see? When you see as the pressure increases, as the temperature increases, the pressure also increases. The volume is constant. Volume is not changing. Volume not changing because they are sealed. So the containers, they are just all like, metallic containers. So volume not changing, but something else is changing. As the temperature increases, what happens? The gases, they begin to collide against the walls of the container. So the collisions in the gases increase. The collisions in gases increase. And when the collisions increase, that means the kinetic energy increases. And when the kinetic energy increases, the motion in the particles, the motions, that's the collisions, that increases. That means the pressure increases. That means they hit the walls of the container with great force when the temperature, anytime the temperature increases. Okay, so temperature increases, the collisions in the gases increase, kinetic energy increase, motions in the gas increase, and the pressure increases. So this is one thing. And when the temperature goes down, vice versa. Okay, so this relationship has been explained as by this formula, which is P1 over T1 is equal to P2 over T2. And P1 is pressure, T1 is the temperature. Now, that means that the relationship is the, just note down here that there's going to be the thermometers, obviously, with these things will read the thermometer, these thermometer readings, okay, will tell you what is the temperature and what is the subsequent volume. So you increase the temperature, you read the volume, you increase the temperature, and of course, there's a limitation. There's going to be an explosion at some point. However, we see that there is a direct relationship between the pressure and temperature. When the pressure goes up, when the temperature goes up, the pressure also goes up. And when the temperature goes down, the pressure also goes down. All right, now let's do this problem. This is problem, the study check 8.5, and this is a problem 301. Oh, sorry, page 301. Page 301. Okay, here in a storage area of a hospital where the temperature has reached 55 degrees Celsius. So temperature given is 55 degrees Celsius. Always, always, always convert. And I'm going to write this down here. Always, always convert degrees Celsius to Kelvin by adding 273. By adding 273 to degree Celsius. Okay, so here we are going to add 273 to this, plus 273. So you get here 8, and this is 712 and 328 K. So always do that first. Okay. In a storage area of a hospital where the temperature has reached 55 degrees Celsius, the pressure of the oxygen gas in a 15-liter cylinder. So just note down the volume somewhere, although the volume is constant, but this is a 15 0.0 liter cylinder, and the gas is oxygen gas. So it's good to have the identity of the gas also. Steel cylinder is 965 torr. So the pressure is 965 torr. And note this down, torr. Okay, to what temperature in degrees? So next question is, to what temperature in degrees Celsius? So they want it in degrees Celsius. Would the gas have to be cooled to reduce the pressure to? So the next pressure is 850 torr. So one thing important is to always note down the units, okay? Units have to be noted down, okay? When the volume and the amount of gas do not change. So now the only thing here is that we will still do the conversion, but we will convert it back to the degree Celsius, because that's what they want. Okay, so let's do this. So here we have the formula P1 over, so we need to find the T temperature. So let's put this here, sorry. This is T1, this is T1, P1, and this is T2 and P2. So here we need to find T2. So P1 over T1 is equal to P2 over T2. And since we need to find T2, so this is like double like transformation. So here, so first bring T2 this side. So P1 over T1 times T2, because we need to find T2 on one side, but we need to get rid of T2 here. P2 over T2 times T2. So here, this cancels out the T2 from this side. Okay. Next is we need to bring the T2 only on one side, because, and then we need to get rid of P1 over T1. Okay. So in order to do that, you're going to create a reciprocal T1 over P1 times T2 is equal to P2 times T2 over P1. Sorry, T1 over P1. T1 over P1. So here you will see that the T1 and T1 cancel out, P1 and P1 cancel out, and you're just left with T2 is equal to P2 times T1 over P1. Now plug in the numbers, which is T2 is equal to P2 is 850 torr, 850 torr. So since they are torr and torr, it's the same, doesn't matter. Then comes the T1. T1 is 328 K over P1. P1 is 965 torr. So the torrs cancel out and we have these numbers. So let's do the math. Okay, so we get the value for T2 as 288.911 Kelvin. Okay, but the question is in degree Celsius. How much it is in degree Celsius? So here what you're going to do, you're going to take the Kelvin minus, 273 minus Kelvin. This T2 value, the Kelvin, yeah, Kelvin minus 273, and you should get the degrees Celsius. So in other words, 288.91 minus 273 minus 273, and that gives you 15.91, 15.91 degree Celsius, and that can be easily written as 16 degree Celsius. So this is how you convert if the question is asking you to find the answer in degree Celsius. You still do the conversion, you know, always do this thing. This is very important. Always convert degree Celsius to Kelvin. Okay. Now let's look at the next problem, which is the combined gas law. So here is the again, I forgot the applications. So here, what is the application of the Lussac law? So the application is, you must have seen the car tires. car tires. If you are filling your gas tires in summer, you should always keep them, fill them less. Fill car tires less. Slightly, little bit, slightly less. But if it's in winters, then you fill the car tires, fill the car tire a little bit more. And again, it's all slightly. So this slightly applies to both. So it's just a little bit. Why? Because during the summers, the gases expand, and during the winters, the gases contract on their own. Gases contract in the winters. So when they contract, then, that space is created, a little bit of vacuum is created. So that is why it's a good idea to fill the car tires slightly more in the winter so that, even they contract, there's still air, there. So it's all temperature dependent. In temperatures are very high, so the pressure of the gas increases, right? But in the winters, the temperatures are very low. So the pressure of the gas is lower. Okay. All right. Now let's look at the combined gas law. Combined gas law. Now, combined gas law combines all the three laws. Okay. And we have P1, V1 over T1 is equal to P2, V2 over T2. So they were able to basically see consistently a relationship, gas laws, all the three gas laws, the Boyles Law, Charles Law, Lussac Law, all the three. So they said, okay, let's combine them. And so if we know the 5 values of the 5 variables, we can find the 6th one. Okay, so basically that's what it is. So let's look at this problem here, study check problem. So let's see, let me just see if I can do little transformations here. Let us say if you just want to find P1, then what would you do? If you were to find P1, then P1 V1 over T1 times T1 over V1 is equal to P2 V2 over T2 times T1 over V1. So in this case, when you do this transformation this way, you get rid of the V1 and T1 from one side and you bring it on the other side. So this is how your next, formula becomes P1 is equal to P2 V2 over T2 times T1 over V1. So that will give you the pressure. So keep that in mind that pressure generally will be either in ATM or in millimeters of mercury. We prefer these two, okay? Volume always has to be in liters. So if you're given something in milliliters, convert it into liters by multiply by 1 liter over 1000 milliliters. Okay, and temperature is always going to be in Kelvin. So we already know that if you have something in degrees Celsius plus 273, and that gives you the reading, temperature reading in Kelvin. Okay, now, so if you have this, now let us say there's another transformation in which you are supposed to find T1. Let us say T1 needs to be found. Then how would you do? Then in this case, you have P1, V1 over T1 is equal to P2, V2 over T2. Okay, so what you're going to do first is we need to find T1. So we need to bring T1 on the other side. So what you do here is multiply by T1 over V1 is equal to P2, V2 over T2 times T1 over V1. Okay, so we see here that you have it brought the T2 and so V1 and T1 on the other side of the equation. Because we need to find T1 now, we need to bring the P2, V2, and T2 and V1 also the other side. So what are we going to do here? Next is you're going to bring the P1 and then here, let's get this first, P2, V2 over T2 multiply by T2 over P2, V2, and here also multiply by T2 over P2, V2, okay? And we need to get rid of V1 also. So multiply by multiply by V1 times T1 over V1. So here times V1. Okay, so you see now that here P2 and P2 cancels out, V2 and V2 cancels out, T2 and T2 cancels out, V1 and V1 cancels out. And here we brought the T2, P2, V2 and V1 we brought on the other side, and we have the P1 also. So basically this is now a new formula, which is on a new transformation, which is P1 V1, just writing it better, over P2 V2 times T2 is equal to T1. This is your new transformation. Okay, so just make sure that you know your algebraic skills are in place, and so the rest of it is just that. So now let's look at this problem, page 304, and study check. So study check is 8.6, okay, and then page 304, page 304. Okay, so here a weather balloon is filled with 15 liters of helium. So write down what all is given to you. Volume is 15.0 liters of helium at a temperature, and again this is helium, so it's good to write down the units, I mean the identity. Helium at a temperature of 25 degrees Celsius. Temperature is 25.0 degrees Celsius. Okay, and a pressure of 685 millimeters of mercury. So 685 millimeters of mercury. All right, what is the pressure in millimeters of mercury? Next, what is the pressure? So this is all P1, T1, V1, okay? What is the pressure in millimeters of mercury? So we are not changing the units for the pressure, okay? What is the pressure in millimeters of mercury if of the helium in the balloon in the upper atmosphere when the temperature is negative? So temperature T2 is negative 35 degrees Celsius, okay? And the final volume is 34. V2 is 34.0 liters, okay? So as usual, you are going to first convert. So we see this is liters and this is liters. This is millimeters of mercury, millimeters of mercury. So the same units. So, you know, you don't change, but change this temperature. So 273 here and plus 273. So basically it's going to minus over there, but this one is 273 plus 25. Let me finish this. Okay, so as you see, when I add 273 to 25, I get 298. And then when I subtract 273 from 35 or 35 from 273, I get 238 Kelvin. Okay, now, so we need to find the P2. So let's write this formula first. Always write the formula. So P2, so P1, V1 over T1 is equal to P2, V2 over T2. So we need to find this guy. And now I'm not going to do all these other steps, you know. So we were just going to put this straight away. P1, V1 over T1 times T2 over V2 is equal to P2. So just put the numbers. P1 is 685 millimeters of mercury. Okay. Times the volume. The volume is 15.0 liters over T1 was 298 K times T2 was 238 K over the V2, and V2 is 34.0 liters. So when you do this, you see that the liters and the liters cancel out, right? And Kelvin cancel out, right? And now you're just left with the units of millimeters of mercury, and that's what you want in this equation. Okay. Now, what you do next is the 685 millimeters of mercury. 685 millimeters of mercury is, just leave that on one side, and 685 times 15.0 times 238, and whatever number you get here, divide that by 298 times 34.0, and let's get that. Okay, so when you do these multiplications and the divisions, you get these big numbers, and when you divide them, then you get 241.35. Okay, and it's 241.35 millimeters of mercury. So your book is just giving you 241, which is fine, but 0.35, it's, I think they dropped it. So that's equally right too. So that is the answer to P2. Okay, so that is now the scenario with the 4 laws. And now we are going to look at another law, which is equally interesting and is the most important one. And that is the Avogadro's law. Avogadro's law. Now, Avogadro actually got angry at especially Boyles and Charles also, because Boyles and Charles, they studied the relationship of pressure and volume and temperature. And the problem with the gases is that these gases, their volumes are indefinite. So he's saying, how can you be so sure about the volume of the gas? And fine, it increases, it decreases, all that's fine. That's the common theme that he saw with all these other different gases also. So the same behavior. So that piece is right. But when you do the quantification, by what magnitude or how much, was the increase, how much was the decrease, and, so there he questioned them. And, it's obvious because gases, their volumes are very, very challenging. Gases will take the volume of whatever container you put them. Gases love to expand. Gases love freedom. Gases cannot be compressed for too long. They will always find a way to get out. So they like to expand. They love freedom. They diffuse. The gases which are very heavy, they move slowly, yet they still move, and eventually they expand, and they hate being contracted. They don't like being compressed. So, that's the nature of the gases. That is why they exert the pressure against the wall of the containers. So that's the nature of the gas. So he wasn't very convinced by, he understood the relationship, but he wasn't convinced about the quantification, that this is the volume, the volume that we have been measuring in the syringes, So he was like, okay, let me do my own thing. So he set up his experiments, and we're going to show you now how that worked. So just let me draw the apparatuses. Okay, so now here's the thing. Avogadro studied the relationship of the volumes of the gases and the number of moles. Okay, sorry about that. Okay, so here we have this Avogadro's law where he studied the relationship of volumes of the gases and the number of moles. Okay, and here he kept the pressure and temperature constant. So in other words, all this was done, at kind of room temperature and pressure. So first thing is, you see all these flasks. Each of these flasks has 1 mole of gas. 1 mole of gas in each of these flasks. The weights are different. So when you have carbon dioxide, the weight is 44 grams. When you have sulfur dioxide, the weight is 64 grams per mole. When you have methane, the weight is 16 grams per mole. When you have ammonia, the weight is 19 grams per mole. Chlorine is 70 grams per mole. And neon is 20 grams per mole. So these are the weights of each of these gases, but each of these gases is 1 mole, which means that each of these gases is containing the same number of particles, regardless of what their weights are. The same number of particles, and those particles are 6.022 into 10 to the power 23 particles. So the gases that are molecular, those particles are going to be molecules. The gases that are, all of them are molecular gases except neon, which is an atomic gas. It's made up of just pure atoms, noble gas, right? So anyways, so now comes the question, what is the volume of 1 mole of these gases? We know their exact number of particles we are dealing with, but what is the volume? If you take these same gases in a 250 ml flask, they are going to occupy 250 milliliters of the volume of that flask. If you take these gases and you put them in a 100 ml flask, it will take the volume of 100 ml flask. If you take each of these gases and you put them in a 500 ml flask, they will take the value of a 500 ml flask. So the volume keeps changing for the gas, right? Because they love to expand and they love to contract, and they take the shape and they take the volume of no matter what kind of container you put them in a cylinder, you put them in a tight tubes, they will just adapt to those volumes. So it's very difficult, or it is impossible to get the volume of the gases in the gaseous state. If they are in the gaseous state, it is not possible to get their volume, exact volume, because they keep changing. That's dynamic. Nature is dynamic. So it's not possible. So we came to that realization. But is there a way that we can find out what is the volume of these 6.022 10 to the power 23 particles? Then at least we have some idea when it comes to matter that, okay, 1 mole of gases occupy this much of volume, or in other words, 6.022 into 10 to the power 23 particles of a gas are going to occupy this much volume. If we know that, then we're good. So how do we know that? There's just no way, like I said, if it is in the gaseous state, you can't. So you have to do the conversion. You have to convert them to liquids. So in other words, you have to put them in cooling baths. So these are the cooling baths. So this is the cooling bath, is like brings the temperature down and it condenses the gases. So the same gases that were roaming around in the gaseous state now condense and form a liquid. And this liquid, now you can measure the volume of a liquid. It's easy. You can measure the volume of solids, you can measure the volume of liquids, but gases is impossible. So the exact volume of gases, or the exact, so what do you do that? So once these gases are condensed, then you take these, condense these gases. So I'm going to just put it here. Sorry. I'm going to put this here, that condense these gases, each of these gases, by putting them in cooling baths. Okay, in cooling bath. Cooling bath is just cold, low temperature. So once they are condensed, they convert from a gas to a liquid. Okay, next what you do, you take these liquid from each of these, containers in one container at a time, or one gas at a time, and this is the graduated cylinder. So the graduated cylinders have a marking in them, and these markings are, they tell you how many milliliters and liters and so forth. So these markings are in, let's say, milliliters. Okay, now you pour the gases here. Pour the liquefied gases, in the graduated cylinder, GRADUATED, graduated cylinder. So when you pour them in the graduated cylinder, then what happens? Here's a very interesting thing. Each of these gases, once they hit the graduated cylinder, these gases occupy only a volume which is 22.4 liters. So this 6.022 into 10 to the power 23 particles. No matter what the identity of the gas is, it doesn't matter. They occupy this much volume. So this is the volume of 1 mole of any gas, okay, will occupy 22.4 liters of volume. So this is also called a molar volume. This is also called a molar volume, or the volume of 1 mole of a gas. So each of these gases occupied the same. This is remarkable. Each of these gases occupied the same volume. It's amazing, just amazing, right? So that's what happened, whether it's carbon dioxide in a liquefied form, sulfur dioxide in the liquid form, methane, ammonia, chlorine, or neon, so each of them still had the same. So this is called a molar volume. Okay, now let's look at these problems. The study check problem. We need to put this thing. So it is we see as there's another thing here, as it's a common sense. So volume is directly proportional to the number of moles. So as you increase the number of moles, obviously the volume is going to increase. If you decrease the number of moles, the volume is also going to decrease, So how do you express this? It is V1 over N1 is equal to V2 over N2. Okay, so then let's do the study check problem. The study check problem is study check 8.7, and this is problem 305, page 305. Page 305. Okay, now here we see a sample containing 8 grams of oxygen. Now, very important, if something is given to you in grams, you're going to convert it into moles. So here's this example, oxygen gas, okay, 8 grams, 8.00 grams. A sample containing 8.00 grams of oxygen has a volume of 5 liters. So volume is 5.0 liters. What is the final volume in liters? So this is V1, V2. What is the final volume in liters after 4 grams of oxygen has been added? 4.00 grams of oxygen has been added to 8.00 grams. So a total of 12.00 grams of oxygen in a balloon if the temperature and pressures do not change. So this is the initial volume, this is the initial moles of oxygen. This is oxygen. So this is the initial moles. Initial moles, 8 grams of oxygen is occupying 5.0 liters. So 12. So this is now becomes N2. So this is not actually the moles, but you will have to convert them that relate to that. So that relate to that. So 12 grams. So that is N2. Okay, so first is always convert, always convert grams to moles using the molar mass. Okay, so molar mass. So oxygen is 16 grams, right, per mole, but this is only one atom of oxygen times 2. So this 2 oxygens. So this becomes 32 grams per mole. That's the molar mass of oxygen. Okay, so let's do the conversion. In the first case is 8.00 grams oxygen times 1 mole, and that is divided by 32 grams of oxygen. Okay, so this is one thing. Next is 12.00 grams of oxygen times 1 mole of oxygen divided by 32 grams of oxygen. So let's do the math here. Okay, so this is what we get when you do the divisions. 8 divided by 32, you get 0.25 moles of oxygen. 12 divided by 32 gives you 0.37 moles of oxygen. The rest is just plug it into the formula. V1 over N1 is equal to V2 over N2. And V1 over N1 times N2 is equal to V2. So rest plug in the numbers, which is 5 liters divided by 0.25. So 5.0 liters divided by 0.25 moles of oxygen. Okay, liters of oxygen. So always write down in what context. Times the N2 is 0.37 moles of oxygen. Okay, and then what do you get here? Let's do the math. Okay, so here we see the moles of oxygen and the moles of oxygen cancel out, and you're just left with the liters of oxygen. So when you do the math, you get 7 points. So this is the V2, comes out to be 7.5 liters of oxygen, O2. Okay, so that is 7.50, actually 7.50 liters of oxygen gas. All right, now that is the about this. So it's a common sense. If you increase the number of moles, the volume is going to increase. You decrease the number of moles, the volume will decrease. So, but just keep this in mind about this transformation. Now comes the concept of STP. What is STP and the molar volume? So the STP, standard temperature and pressure. So the standard temperature, like the temperature, the value of the temperature is T, and the value is 273 Kelvin. 273 Kelvin. And this also is equal to 0 degree Celsius. That's the temperature at which the ice, the water freezes. Next is the standard temperature pressure. So pressure, P-R-E-S-S-U-R-E, pressure is equal to P, and that pressure is equal to 760 millimeters of mercury. And this pressure also most commonly used is 1 atm. Okay, now when it comes to moles, how many moles are standard? Only 1 mole is considered to be standard. And what is a volume? The volume is 22.4 liters. That is considered to be standard. So this piece is called the molar volume. This piece, molar volume, volume of 1 mole. Okay, now let's look at this problem here. This is the study check problem, and that is page 3. So page 307, and this is the study check 8.8. 8.8. Okay, so what do you get here? So we see that how many grams of nitrogen? Question is how many grams of nitrogen? Okay, how many grams of nitrogen gas are in 5.6 liters of nitrogen at STP? So anytime the word STP comes, so always you're going to use STP whenever stated in the question, use these values. All right, so for the STP, you do that. But remember that if you have, it's always the moles. It's always the moles, not the grams. But if you get the grams, then you convert them. If you get the moles, the answer question is asking you in grams, then you convert that to grams. Okay, so here we need to find how many grams of nitrogen gas. But we are given 5.6 liters of nitrogen gas as at STP. So anytime something is at STP, it means that 1 mole of any gas is 22.4 liters, or 22.4 liters make 1 mole of the gas. So 1 mole is equal to 22.4 liters. Okay, so that's our concept of STP. So we know that. First, let's find out, first of all, find the moles of nitrogen in 5.6 liters using molar volume as conversion factor. Okay, so here you are going to put 5.6 liters of nitrogen gas multiplied by 1 mole of nitrogen over 22.4 liters. So let's get the moles of nitrogen gas. Okay, so we see that 5.6 divided by 22.4 liters gives you 0.25 moles of nitrogen. Okay, so with that said, now the question is asking how many grams of nitrogen. So next is convert moles to grams. Convert moles to grams. Okay, so using what? Moles to grams? Using the molar mass. Okay, using the molar mass. So in the case of nitrogen N2 is equal to 14 grams times 2 is equal to 28 grams per mole. Okay, so now you're going to take the moles, 0.25 moles of nitrogen times. Now we need to find get rid of the mole. So 1 mole of N2 is equal to 28 grams of N2. Okay, so now moles of nitrogen cancel out and you're just left with the grams. So let's do the math. Okay, so 0.25 times 28 gives you 7.0 grams of nitrogen gas. And that's the answer. Okay, so it's all through practice. So you guys ideally should do the extra credit problems first. So this way, you get the idea. Okay, next is the ideal gas law. Now, ideal, when you combine all these laws, now all these laws, when they combined, then they gave rise to the ideal gas law, where we accounted for all these things that we are keeping constant. So here in the case of Avogadro's law, we kept the pressure and temperature constant, right? Let's just go back. And when we combined, when we have the Boyles law, we kept the temperature constant. We had Charles, we kept pressure constant, Lussac, volume constant. Avogadro's is pressure and temperature constant, right? And then even the, so temperature and pressure constant. So all these constants, then mathematically, and again, this is all comes through derivations, and there are other pieces, to it, which is beyond this course, but you should just know that the value of R, ideal gas law, includes the ideal gas law is PV is equal to N R T. Now here, note this. When the pressure is in ATM, then the value of R is 0.08206, 8206 liters time atmosphere per mole K. Okay, this is one piece. When the pressure is in millimeters of mercury, then the value of R changes. R is equal to, in that case, 62.4 millimeters of mercury. So let's just do this, liters times millimeters of mercury over mole K. Okay, so that thing. Next is the value of N. N is just the number of moles. So if you are given the grams, you should always convert to moles using the molar mass. Okay, always. So that's one thing. Next is the volume. Volume always has to be in liters. So if the volume is given to you in milliliters, convert it to liters by multiplying by 1 liter over 1000 milliliters, and that will convert it into liters. And RPV and RT and temperature. Temperature always, always, always in degrees. So if it is something in Celsius, you have to convert to Kelvin. So here's this Kelvin. And if something is in Celsius, then you add 273, and that will give you the Kelvin. So these conversions are important for the ideal gas law. Now let's look at this problem here. This is in study check problem 8.9. So study check 8.9, and that is page 309. Page 309. Okay. Now page 309. So here, chlorine gas, chlorine Cl2 gas is used to purify water. How many moles of chlorine gas are used? So we need to find the value of N for chlorine gas are used in a 7-liter tank. So volume given is 7.00 liters tank. If the gas has a pressure of 865, so the pressure given is 865 millimeters of mercury, 865 millimeters of mercury, and the temperature is 24 degrees Celsius. So convert this 24 degrees Celsius to Kelvin, multiplying by, adding 273. Okay, so this becomes 7 and 7, 8, 9, 297. Okay, so 297 Kelvin. Okay, now we need to find the value of N. So here is this PV is equal to nRT. So when you do the rearrangement, this becomes PV over RT is equal to N. Now here's something that is missing or will not be given to you, but you should know, and this is all listed in your handout. So I'm going to just put this here, that the last page here, look at handout, the last page, one of the last pages. So it's on the last pages. All these laws are listed, okay? So you can forget them, and then values of R and all that is listed. But if something is missing, please add yourself. That's always like, you know, you need to put your own notes also. Okay, anyway, so here we have the value of R. Because this is given in millimeters of mercury, therefore we are going to use 62.4 liters times millimeters of mercury per mole K. Okay, so we are going to use this value. Okay, these values, it's important. Now we have pressure is 865 millimeters of mercury, okay, times the volume is 7.00 liters, divide by 62.4 liters times millimeters of mercury per mole K, okay, times the T, the temperature is 297 K, 297 K, and that is equal to N. Okay, now we have the millimeters of mercury cancel out. Liters and liters cancel out. And then moles we need to find, K and K cancel out. Okay, now you just do the math here. Let's do the math. Okay, so we get this number is 865 times 7 gives you 6,055. And then when you multiply 62.4 with 297, you get 18,532.8. And when you divide 6055 by 18532.8, you get 0.3267 and so forth moles. Okay, and that is the moles of chlorine gas. Okay, so that is one piece. Now, next is, let's do this using the same formula. We are going to use the study check. Look, let's look at the study check 8.10, and then the 8.10 and then the page is 310. Page is 310. Okay, now here what do you see? We see here that what is the volume? So volume in liters of 1.20 grams. So grams of CO2 is given, and the grams of CO2 is 1.20. Okay, CO2 grams of sorry, not the CO2, carbon monoxide. Sorry about that. This is not CO2, it's carbon monoxide. Okay, carbon monoxide gas at the temperature given is 8 degrees Celsius. Okay, if it has a pressure given is 724 millimeters of mercury. Okay, now here we have the volume we need to find, but the grams of CO2, these grams of CO2, we need to convert them to moles. So convert, that's the first thing. Convert the grams of, I keep saying CO2, I'm sorry, it's the carbon monoxide. I'm sorry, carbon monoxide, grams of carbon monoxide to moles. And we are going to need the molar mass of CO to moles. So carbon, there's only one carbon, there's only one oxygen. Carbon is 12, oxygen is 16, and that gives you 12 plus 16 is 28 grams per mole. Okay, so 1.20 grams of carbon monoxide times 1 mole of carbon monoxide over 28 grams of carbon monoxide. All right, so here you have the grams of carbon monoxide and grams of carbon monoxide cancel out, and you get the moles of carbon monoxide. Let's calculate that. Okay, so you see that here we have the moles of carbon monoxide, and the moles of carbon monoxide comes out to be 1.20 divided by 28 is 0.042 moles. Okay, now here also I've done the conversion of the degrees Celsius to the, add 273, and this will give you the Kelvin 281. So we have that. Another thing that is never going to be mentioned, but we expect you should know the value of R, which is 62.4 liters times millimeters of mercury over mole K. Okay, now we will see this, that we need to find a volume. So PV is equal to N R T, or in other words, volume is equal to N R T over P. So just use this formula. So, and plug in the numbers. So volume is equal to N R T over P. N is 0.042 moles, okay, times 62.4 liters times millimeters of mercury per mole K times the temperature. The temperature is 281 K. So 281 K. Divide all of this by the, what was that? Pressure. And the pressure is 724 millimeters of mercury. 724 millimeters of mercury. So here you are going to divide, cancel out. The millimeters of mercury cancel out. Moles and moles cancel out. K and K cancel out. And you're just left with the unit of liters for the volume. So now we have the volume is equal to 0.042 multiplied by 62.4 times 281. Divide this whole thing by 724. And you are going to get, let's do this math. Okay, so when you do the math, you get 736.44 divided by 724, and the answer is 1.01 liters. The book is saying 1.04, which is fine, maybe somewhere in the decimals. So anyways, then that's another thing is like this number right here, 273, is actually 273.15. So, but we just commonly we use 273, but that number is also used, but that's more exact, like I'm saying. Okay. Anyways, now we're going to look at the gas stoichiometry, and then the last part is the Dalton's law of partial pressure. Let me do the Dalton's law of partial pressure first, because that's all these laws are coming. So let's do this one first. So here is the Dalton's law of partial pressure. Okay, Dalton's law of partial pressure. So very common sense law and a very interesting law. So here he says that the total pressure of all the gases that are inside the container is actually the sum total of the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and so forth. So in other words, what it means is that if you take a balloon, and in the balloon you fill all these different types of gases. So let us say you have a gas which is, let's just give it a color to it, like a little gas. Let's say this is gas A. Then let's say another gas is this gas B. It's actually made up of this piece right here, is gas B. And let us say this is gas C, gas C. Okay, some gas C. And this gas C is hitting the walls of the container with some force. Gas B is also hitting the walls of the container with some force, right? And A is also hitting the walls of the container, the walls of this balloon with some force. So each of these gases have a mass. Remember that. This gas has a mass, this gas has a mass, and this guy also has a mass. And that mass, you know, is going to make these gases like apply that force, you know, that it's going to play a role there. And also it's going to affect the speed with which they hit the walls. So the speed and the force, you know, which with, you know, force basically is the pressure. Force is equal to is a pressure each of these gases are exerting, right? So the total pressure is the partial pressures of each of these gases. So partial pressures are obviously going to be small. Partial pressure is, you know, a smaller number. But P total is the sum total of all the partial pressures. So P total is the sum total, or you add up all these partial pressures. So sum total of all partial pressures. Okay, so this type of application is the application of this is in anesthesia. You know, what is in your lungs, what's the capacity in your lungs. Also in deep sea diving also, where they take helium and oxygen mixed together. So here, deep sea diving. Okay, when they're making these, you know, gas cylinders. So gas cylinders, they use oxygen gas, and then they mix it with helium. So how much should be the oxygen gas? How much is the helium? You know, all that, you know, is all the partial pressure of these gases. Okay. Each of these gases exert. And then also the other application is in anesthesia, anesthesia. I may have missed the spellings, but anesthesia, you know, how much of those gases should be given and what's the capacity of the lungs and all that, you know, all those other technical details, which I'm not aware of, but that's one. Hyperbaric chambers is another one, where how much of the oxygen needs to be given, you know, so hyperbaric chambers, you know, where they are giving these oxygens to the patients, you know, because there are other gases also, but how much of that oxygen should be given, all that comes through this very complex law. Actually, it's simple, it looks simple, but you know, math is simple. But let's look at this now. All right, so this is the second last problem here, and this is, oh, where's the study check problem? Oh dear. Okay, a study check. Okay, here is the study check. .12. Okay, and this is page 313. Page 313. All right, here we have an anesthetic consists of a mixture of cyclopropane gas. Okay, so this is here cyclopropane, which is C3H6. Okay, C3H6. So this is the cyclopropane gas and the oxygen gas. Okay, if the mixture has a total pressure, so P total given, P total is equal to 1.09 atm. Okay, and the partial pressure of cyclopropane, so P, the C3H6 gas, the partial pressure of cyclopropane is 73 millimeters of mercury. So obviously you see that the units are not matching. So you need to change that. What is the partial pressure of oxygen in millimeters of mercury? So millimeters of mercury, okay, millimeters of mercury in this anesthetic. So first thing is we need to change this ATM to millimeters of mercury, because the question is asking us in millimeters of mercury. So change this to here, millimeters. So here we have 1 ATM is equal to 760 millimeters of mercury. Okay, so we have 1.09 ATM multiplied by, now here you have 760 millimeters of mercury over 1 ATM. Okay, so here we see the ATM and ATM cancel out, and you are left with 1.09 times 760. 1.09 times 760, and you are going to get 828.4 millimeters of mercury. So this is the one that is P total, that is the total pressure. You will use this. Okay, so now let's just put this numbers here, that P total we already know is equal to P of oxygen plus C6, the partial pressure of C3H6, partial pressure of C3H6, or in other words, P total minus the P C3H6 is equal to P of oxygen. Now just plug in the numbers, 828.4 millimeters of mercury, always write the units, minus the pressure is 73 millimeters of mercury, 73 millimeters of mercury, and that gives you the partial pressure of oxygen. So that comes out to be 755 millimeters of mercury. Okay, so this is how you will do these problems. And now the last part we're going to do is the gas laws and the chemical reactions. Gas laws and chemical reactions. So basically stoichiometry of, you know, these reactions where the gases are evolved. Okay. All right, so here we have, let's do the study check, because stoichiometry you have already done. So, I mean, it's the same thing. Okay, here we have 8.11. Okay, study check 8.11, and page is 311. All right, so let's look at this problem here. You are given 2 moles of aluminum as a solid, and that is reacting with 6 moles of HCl as a aqueous solution, and that is giving you 3 moles of hydrogen as a gas plus 2 moles of AlCl3 as an aqueous, it's in the aqueous medium. So in other words, we are focusing on, since this is a gas laws chapter, so gas, hydrogen gas. Okay, so now the question is that if, let's write this down here. If 12.8 grams of aluminum, so given 12.8 grams of aluminum reacts with HCl, how many liters of hydrogen, so volume of hydrogen in liters, would be formed at the given temperature is 700, so the pressure given is 715 millimeters of mercury, 715 millimeters of mercury at 19, and the temperature is 19 degrees Celsius. So by default, convert the 19 degrees Celsius to Kelvin, so 273. So just don't forget that part. So 273 plus 19, and that gives you 290 2K. Okay, so there are two steps in this problem. The first step is find the moles of hydrogen. Okay, find the moles of hydrogen. That's one thing. And how would you do that? Using moles of aluminum, right? Through stoichiometry, which we did in the previous chapter. All right. Next is, once you get the moles of nitrogen, no, sorry, the moles of hydrogen, then that is going to be the value of N. Okay. Then PV is equal to N RT. All right. So we need to find the volume, right? We need to find the volume. Volume is equal to N RT over P. Okay, so just plug in the numbers. So let's do this. So here you are given 12.8 always. So first is take find the moles of aluminum. So 12.8 grams of aluminum, okay, to moles of aluminum. Then times the mole to mole ratio. Mole to mole ratio. So the moles of hydrogen over the moles of aluminum. So that's going to give you the moles of hydrogen. Okay, so let's do this. The molar mass of aluminum is 26.98, so it's 27. So this is using the molar mass of aluminum. So let's do this. 12.8 grams of aluminum times 1 mole of aluminum. 1 mole of aluminum, okay, over 27 grams of aluminum times, now mole to mole relationship, moles of hydrogen and the moles of aluminum. So the moles of aluminum are 2 and the moles of hydrogen is 3. So you're going to put this here, 3 moles of hydrogen coming from the balanced equation over 2 moles of aluminum. So if you look now that the grams of aluminum cancel out, moles of aluminum and moles of aluminum, cancel out. So what do you get here? You get 12.8 times 1 times 3 divide by 7 times 2. And let's do the math. Okay, so we see that we get doing the 12.8 times 3, and then that gives you 38.4, and then 27.2 gives you 54. So you get the 0.711 moles of hydrogen. Okay. Now, the next step is you take these moles of hydrogen and moles of hydrogen and you put them in the formula. PV is equal to nRT, and we actually already did that, so sorry about that. So here is your PV is equal to nRT, and we need to find, we already did this conversion, volume is equal to nRT over P. Volume is equal to nRT over P. Okay, now N is equal to 0.711 moles. Okay, now R, because the temperature, the pressure given is in millimeters of mercury, therefore the value of R is equal to 62.4 millimeters of mercury per mole K. Okay, so this is the value we will use, 62.4 millimeters of mercury times L over mole K times T. Temperature is 292 K. 292 K. Okay, over the pressure, and the pressure given was 715 millimeters of mercury. 715 millimeters of mercury. Okay, so let's see, first of all, the units canceling or not. So millimeters of mercury and millimeters of mercury cancel out, right? Moles and moles cancel out, and K and K cancel out, and you're just left with the unit of liters, and that's what you need to find. This is the volume in liters. Okay, so now you're going to take 0.711 times 62.4, like the liters is obviously out, times 292 over 715, and you are going to get the answer 18.1 liters. Okay, that is the volume in liters. All right, so this finishes this chapter, and if you guys have any questions, don't hesitate to ask me, and I'm always there to help you. So if you want to see me in the office hours, you can come and stop by also. But other than that, I mean, in general, everyone seems to be doing fine, but I'm there to help you. So don't hesitate. Okay, guys? All right. So thank you for watching. Take care. Bye-bye.